Welcome, everyone, and thank you for attending the last NCMA Technology Team webinar for 2020. Our special guest today is Dr. Scott Smith, who will present on chip breaking using NC programming. Dr. Scott Smith is a group leader for intelligent machine tools at Oak Ridge National Laboratory. His research areas include high-speed machining, process optimization, and machine dynamics. He has taught numerous industrial short courses, and he holds 11 patents. Without further ado, Dr. Smith, welcome and thank you.
Well, thank you for having me. It's a real pleasure for me to be here. I think that I am sharing my screen now, so you should be able to see my presentation. So what I'm going to talk about is chip breaking using NC programming. So as you heard, I am the group leader for intelligent machine tools at Oak Ridge National Laboratory. Specifically, I'm in a facility that's called the Manufacturing Demonstration Facility. So this is not on the main campus. This is outside of the fence at Oak Ridge National Laboratory, and that's on purpose. We have a lot of industrial partners that work with us, and they have easier access because of that. This is a photograph that shows the outside and the inside of our facility. Actually, it's considerably more full now than it was when the photograph was made, but you get some sense of the scale that's there. So the manufacturing demonstration facility has a long history in additive manufacturing, so about a decade or so. They came to the realization that many of the parts that they were making by additive processes, maybe most of the parts that they were making by additive processes, still needed machining. And so about a year and a half ago, maybe almost 2 years ago now, they hired me to start the Intelligent Machine Tool Group. So I'm the new kid on the block. Before that, I was the department chair for mechanical engineering over at the University of North Carolina at Charlotte, where there was a pretty big machine tool program as well. I've been a machine tool researcher for about 30 years now. And so there's a lot of interesting things going on. If we ever get to a place where we can travel again, you're certainly all welcome to come by and visit us. In a normal year, the MDF would get something like 6,000 visitors. So you're all welcome, presuming that we get to a place where we can travel again. Okay, within my group, just so you have some sense of where this project falls, there's sort of 3 big thrust areas. And the first area would be making better use of the existing installed machine tool base in the US. And so this whole class of projects is what can I do right now so that people can make better use of their existing machine tools. And I feel like that's almost an emergency, right? What can I do to help right away? This project that I'm going to talk about today falls in that category. The second big category would be creating new machines for new needs, machines that don't exist for the things that we want to do. And you can see there in some of the photographs that would include hybrid machine tools, additive and subtractive in the same machine, but would also include things like small machines making big parts. And you can see sort of a cartoon picture of one of the machines that we have in mind for making a large scale linear component. And then on the right of that, you can see a photograph of the machine under construction. We also do some effort in workforce development. And I don't mean that we're competing with universities. We're not teaching classes and giving degrees or anything like that. But we are trying to do things to help the whole spectrum of the workforce. And that's everything from people who operate machine tools to the ones who design them and write the software, and the entrepreneurs who are going to start the companies, and everything in between. So those are sort of the 3 big thrust areas. And like I said, the project that I'm going to talk about today falls in the first category. How can we make better use of the existing installed machine tool base? Okay, so you probably know that unbroken chips often pose problems for single point cutting operations. If you've been around machine shop at all, you have certainly seen these kinds of problems. These are all pictures of turning operations. And the problem that frequently happens is that the chip that's being removed from the workpiece doesn't break. And it just gets longer and longer. It gets tangled all up on itself. It gets wrapped around the tool. It gets wrapped around the workpiece. Very often the operator has to stop the machine to remove it. Surprisingly, it is one of the more common sources of injury in a machine shop because the chips are often sharp and it's tempting to try to reach in and grab them. And so the chips might, the tangled chips like this might spoil the workpiece. They might damage the tool. They might injure the operator. And for sure, they don't move well through the chip conveyor system. And they're just generally a problem. So what can we do to stop that from happening, right? A lot of people call this the bird's nest, right? How do we stop the bird's nest? Now people have worked on this for some time, and there's some neat ideas. I'm going to show you a picture of a little video that shows one of these long stringy chips forming. And you can see it getting all curled up there, and it wraps around on the front side of the workpiece. And we'll see it a few more times before it eventually breaks. Right, but this is the problem, right? And eventually it broke off, but now we start another one, right? And they can get tangled around each other and so on. So what are we going to do to stop that? I want to take the chip that you see in the bottom, in the center of this photograph, and make it more like what is in this person's left hand. Tiny little broken chips that don't tangle on each other and are easy to move around, right? Left hand in this picture is good, right hand in this picture is bad. So there's a lot of strategies. So one strategy would be to use a chip breaker. All right, I'm not 100% sure if you can see my mouse, but I'll point with it here. On the left, you can see there is a turning insert that's clamped into a tool holder, and it has this special geometry around the edge. And the purpose of that is to turn the chip back on itself so that it collides either with the workpiece or with itself, or it has a sharp enough radius of curvature that it cracks and breaks, right? We call those chip breaker geometries. Now, very often that's included in the insert. It's molded into the insert. It could also appear as a little piece of material that you clamp into the holder with the insert, and that's what you see in the picture there in the bottom with the cross hatching on it. There is an adjustable chip breaker that's clamped in beside the insert, so as the chip came along, then it curls up and causes it to break. Another idea is what you see immediately to the right of that, high pressure coolant directed right at the cutting zone. And so you can see the tool there, and the dark purple is the high pressure stream of coolant, and it's sort of shooting right down the cutting edge. And it does two things. One is that it cools the chip, and by taking a lot of the heat out, it makes it a little more brittle, more likely to break. The other thing is that it puts some pressure to push the chip away from the tool, and so that often works. But you have to have specialized equipment to produce the high pressure stream of the coolant. There's another picture of that just to the right. So again, similar idea. There's even been some attempts at mechanical devices to cause the chips to break. This is an interesting patent that I found. This is for the outside turning of a cylindrical bar. You can see that held in the spindle of a lathe, and included on the saddle with the tool post, there is this cam with a motor that drives it, and that cam causes this end of that bar to rock back and forth, and it makes the tool engage and disengage the workpiece. So when I saw this, it started me thinking about whether there might be another way. Maybe there's a way that I can always cause the chips to break. And the basic idea is this: can we change the part program and use the axes of the machine tool to modulate the motion of the tool along its intended path and absolutely cause the chips to break all of the time. So the picture on the left here that indicates that is greatly exaggerated. The motion, you'll see later on, I have some video. The motion is not nearly that big, but I'm trying to illustrate the concept of what's going on here. So this is a profile turning operation, right? I'm taking a cylinder from one diameter to another. And as the tool moves along the direction toward, parallel to the axis of the spindle toward the chuck, then I'm superimposing a sinusoidal motion on it. And it's part of the NC program. And so the surface, if I think about like unrolling that picture of the surface, then I get what I see on the top right here. And the blue line would be what the tool did in the first pass, right? That's the wavy surface that's being created. And then the next time around, the tool is following the red path. And so you can see right here, this green dot is when the tool engages with the workpiece. And so in all of this zone, there is material being removed all the way down to the place that's marked B. And now the tool loses contact with the workpiece. So the chip absolutely breaks because the contact with the workpiece is lost. And so in this portion of the motion, then there is, you can see no chip being removed at that time. Okay, let me get this. Yep, something popped up on my screen here. Let me get that out of my way. Okay, so it absolutely works, but not, I have to arrange it correctly, right? You can imagine that if this wave that I'm producing on the surface that really doesn't show up on the finished surface, right? The motion that I am including there is into and out of material that's being removed, but it's parallel to the surface that I want to create. So you can imagine if the motion of the tool exactly lines up with the motion one revolution ago, then I'm not going to break the chip, right? The two waves are exactly aligned with each other, and that would be bad. So I'm trying to illustrate that in this case, right? What kinds of conditions cause the chips to break? What kind of speed do I have to run? What demands are put on the machine, and so on. And so what I'm illustrating here is the first pass around the workpiece as the blue line or the purple line that's there. You can see it starts at the tool position 0. And then the next pass is the green line. And so you can see the feed per revolution there is 3,007 inch. But the amplitude of the motion that I am superimposing on it is a little less than half of that. And if I do that, even in the most favorable alignment for chip breaking, right here between the green and the blue line, you can see it gets really small. The chip gets really small, but the chip never actually goes away. And so this, in fact, is not guaranteed to break the chip. So under what conditions will it happen that the chip is guaranteed to break? You can see if it was lined up a little differently, like this other green line, that the chip stays pretty thick all of the time, right? If that was the alignment, then that chip doesn't break. So how do I determine the conditions where a chip will break? Okay, so it's going to depend on a few things. One is, and we can see it on this picture, one is the amplitude of the motion that I superimpose. And that's the thing that's marked A in the picture, right? What's the size of the motion that I'm superimposing? Another thing is what's the nominal feed per revolution, and that's the F with a subscript R. The ratio between those, we call that the ratio of the amplitude and feed, RAF. And in this case, in the picture that I have here, it's 0.48. So not quite, the motion that I superimpose is not quite half of the feed per revolution. Okay, so I start looking at this and I imagine how it might be. Let's imagine that the amplitude that I superimpose got a lot bigger. Let's say it's twice as big as the feed per revolution. Then again, the blue line indicates what the position of the tool was the last time around the workpiece, and the green line is what the tool is doing now. So if they were exactly lined up like this dark green line, then the chip doesn't break, right? The thickness almost doesn't change because it's exactly synchronized. But if I could shift it a little one way or the other by not having an integer number of waves per revolution, right? Then I can cause those two lines to intersect, like over here at the 0, and then back over here where this red dot is, and then back over here. And so I'm cutting, and then I'm not cutting, and then I'm cutting again, and then I'm not cutting, and that will absolutely break the chips. It turns out that the shift, the alignment change that I make between these depends on how big the motion is. The bigger motion that I apply, the less change I have to make in the alignment in order to make them break. So here's a picture when it's when the ratio of the amplitude to the feed is like 10. So now I only have to make a tiny little misalignment between one revolution and the next in order to cause the chips to break. So it gets easier and easier to break those chips as the motion gets bigger and bigger. Okay, so there's a calculation that goes along with this. I won't go through all the details of the calculation unless somebody really wants to see them, but I can show you that it comes out relatively straightforward for me to understand when the chips break and when they don't break. And this is all a few slides which are sort of illustrating that calculation. You can see the alignment here. Green would be the first pass around the workpiece. I'm sorry, blue is the first pass around and green is the next pass. And so in this condition, you know, I'm cutting all out in this area, and then there's a small area where I'm not cutting, and then a big area where I'm cutting, and then a small area where I'm not cutting, and so on. So it turns out this is the end result. The phase, the misalignment that I have to have in any revolution depends on the feed per revolution and the amplitude of the motion that I am superimposing. Bigger motion makes it easier. Smaller feed per revolution makes it easier. But that's the expression that defines it. But okay, I'm a visual person. What does that mean? Here's what it means. On the horizontal axis, this is the ratio of the amplitude that I am superimposing to the nominal feed. So bigger number means a bigger motion, right? 1 means it's as big as is the feed per revolution. 7 means it's 7 times bigger than the feed per revolution, right? That's along the bottom scale. On the vertical scale, that's the phase shift that's required. But you could think about that like the number of waves per revolution. So at the bottom, so effectively this is, so the 0 means that the frequency of the motion is 0, so the tool's not moving, and so that looks just like regular turning, right? The top, that actually means exactly 1 cycle of the motion per revolution, and that means that the wave and the motion of the wave left on the surface and the motion of the tool are just exactly lined up. And in either one of those cases, the chip does not necessarily break. It's back to the normal turning type conditions. But in between, and all the stuff that's over here where it says broken chips in this zone, that's where the breaking happens. So it turns out, in order to insist that the chips break, I have to have an amplitude of motion that's at least half of the feed per revolution. And if it's half, then I have to have the phasing exactly right. I have to have 180 degrees out of alignment in order to make it happen. But as the amplitude gets a little bigger, only a little bigger, then the zone in which the chips break gets much wider. It gets wider fast. And the meaning of that is that it's not very demanding on the machine. Actually, I can make the chips break with relatively small motions and with relatively slow motion superimposed. So this is not like ultrasonic machining. The motion that I'm asking the machine to do is on the order of a few hertz, a few cycles per second. And the size of the motion is on the order of the feet per revolution or so. And then it breaks. And so the result is that most machines can do this. Okay, so looks like it's going to work. This is a picture that shows a different depiction of what's going on. Again, the size of the wave that's on the being left on the workpiece is greatly exaggerated to try to illustrate this. And this is turning on the end of a tube. And so you can see the wave that was left on the surface in a previous rotation, and then the current motion that the tool is making, and then all the places here that are hatched in red, that's where material is being removed. But the chip goes from a thickness of 0 here to a thickness of 0 there, and so it breaks. It comes off, that piece comes off by itself. In fact, it's kind of interesting. If I play around with the conditions, I can program the lengths of the chip. So I know I don't want them really long and stringy, but sometimes I also want them to have a little bit of length, because some people collect them up and compact them. And if they're too short, then when you put them in the compactor, they spring back and don't lock together. So they actually have specifications on the size of a chip that they would like, and I can effectively choose that. You might be curious, there is a patent on this process, so this is described. I'm happy to share that with anybody who would like to see it. But I think probably you would like to see some videos that show the system in operation. And so I'll start with this one. So I'm not sure if you're going to be able to hear the sound. This does come with sound, but this is a facing operation. And now this is without the chip breaking strategy being used. And you can see I'm making a really long stringy chip there. It got wrapped around the tool. Okay, now this is with the chip breaking strategy in place. So the motion of the tool, you can see, is parallel to the direction, the superimposed motion is parallel to the direction of the tool. So in this case, it's parallel to the face. So here's without and with. I thought you might enjoy that one, right? That's pretty terrible, but breaking on the right. Okay, here's another video that again shows the process in operation. So again, this is a facing operation. You can see the big tangle down below the tool there at the bottom. And then here's the same operation, but now with the chip breaking strategy imposed. And so you can see the chips are breaking very nicely and getting out of the way. All right, I have another video here. So this one's going to show a few different operations. I'm going to show the turning on the outside of a cylinder. I'm going to show the turning of a cone. I'm going to show a boring operation as well. So realistically, any of the single point material removal operations that you would do on a lathe, this strategy will work, right? I'm using the machine, so the machine axes are making this motion anyway, so they can move along those surfaces, but I'm superimposing this oscillation on top of that. Okay, so this is turning on the cylinder, and you can see that the chips are breaking. You can actually see the motion of the tool there a little bit. And you see it's not very big, and it's also not very fast. Here it is happening on the cone. Okay, here is a boring operation. So again, a single point operation that you would do on a lathe. Here is the tool moving on the surface of a hemisphere. And again, the motion here is slowed down so that you can see it. The oscillation is parallel to the surface that I'm leaving behind. Okay, so now what's the price that I pay for this, right? The NC program is getting a lot longer, right? If it was just turning on the outside of a workpiece, you know, it would say move the x-axis from here to there, and it's one line of code. And instead, I'm putting in lines of code that specify the motion of the tool back and forth. And so the program got a lot longer. But mostly the controller can handle that. That's not really the limitation anymore. In fact, mostly the controllers are good enough that the calculation that's required could be done in the controller. There's absolutely no problem with that, except we didn't do it yet. But in the same way that you have linear interpolation or circular interpolation, you could also have chip breaking interpolation as well. The calculation is not hard. Okay, so here's another hemisphere being turned. And you can see that the surface here is pretty good. And I will, I'll talk about the surface some more in a little bit, because I know that's going to be one of the questions that many of you might have. Here, I'm going to show video of the process being used to make a drive shaft. And this is a picture of the shaft that's being created and a picture of the setup. It's chucked in the workpiece is in the chuck, and it's being supported by a tailstock on the right side. And then I have just some video that show that from two different angles. So there's no special geometry in this. This is just a flat insert, no chip breaking geometry. But it absolutely always works. It doesn't depend on the material. It works in plastic the same as it works in aluminum or steel, titanium. I'll show you some other interesting materials in a minute as well. Here's a slow motion video that shows it. And you can see the motion of the tool is pretty small. The machine can easily do this. And then there are the chips which were collected in this particular operation. Okay, I'll show you one more. This one is kind of entertaining. You might enjoy. This is a material that the heat of the cutting is enough to make it catch on fire. And so breaking the chips was really important in this case. When they form a big snarl, that's bad. And so here's a few pictures that show the snarl forming. The operator is, ordinarily this would be done with a big flow of coolant all the time. But in this case, the operator is turning the coolant on and off so that we can get a nice view of what's happening there. Right, there's the bird's nest. And you can see it stays stuck to the tool. And so typically the operator would stop the machine to clean this, either pull the chips out manually, or you'll see in this case, knock them off with the coolant. Okay, now here it is with the chip breaking strategy. The material still is hot, and that's still a problem. But in this case, all the chips are small and they fall down into the coolant in this operation. Okay, so what's good about what I showed you? It always works. All workpiece materials, all tool geometries, there's no special chip breaker geometry that's required. The modulation is defined along the workpiece surface, and so it appears in the NC program, it's in the M&G code, and that's much longer than the original program, but it's not hard, and mostly the controller can manage this. For the same metal removal rate, the instantaneous feed rate is higher, right? Because the tool has to advance into the workpiece and then withdraw and then advance and withdraw. And when it does the advance, its instantaneous feed rate is higher. Or conversely, if I'm limited with the instantaneous feed, then it's going to take longer to make the part. But for the applications where this is particularly useful, that's not really the objective, right? I'm trying to make sure the chips break so that I don't have to manually intervene. But I'm sure you have questions, and questions might be, what do the surfaces look like? It might be that the surface is worse because sometimes the waves add up and sometimes they subtract from each other. Or it might be that it's better because the tool goes back and forth over a surface that it already made, so maybe it acts like a wiper. Well, it turns out it could be either. So if I look at the unwrapped motion of the tool, that's what these parallel lines are at the top. And so that's along the workpiece from left to right, and rotation is from top to bottom. And so that looks like the feed marks that you see on the surface in a normal turning operation on a cylinder. When I superimpose the motion on top of that, then it changes. And in some place, the spacing between the tool motion gets really tight, like in this area that's marked in red. And sometimes the spacing is not so tight, like in this area. And so that means that the surface changes as I move along. And if I calculate the surface, I mean, you're all familiar with this calculation. If you take the tool profile and you move it along by the feed per revolution, and you get these cusps, the feed marks that you see on the workpiece, so those are there, and I can compute them for the new tool paths that I'm suggesting. And so conventional looks like on the top, that's the surface that would be left behind, and the one that I'm creating is on the bottom. And so in this case, I made the surface worse. So that's a bad alignment. But that's not always the case. Sometimes it's better because the tool goes back and knocks some of those peaks off, right? So it acts like a wiper. So if you look over the whole possible range, then you get a picture that looks like this. And it's a really nice, colorful picture. And what you can see, on the right-hand side, this is no oscillation at all. So that's just regular turning. And then this dark blue valley that runs right there where it says 1, that's exactly 1 cycle per revolution. So that's the picture that I showed you earlier. And the chips are breaking in this zone, and they're not breaking outside here where it's deep blue. But deep blue would be good. Deep blue is the surface finish. And so blue is better, red is worse. So within the zone that these chips are breaking, there's some bad places, but there are also some good places. Let me zoom in and look where those, where those good places might be. So I'm zooming in and by the way, this line occurs at 1 wave per revolution. This one occurs at 2 waves per revolution and 3 waves per revolution and so on. So they look just like each other. I'm going to zoom in and look at this one. And I can see that there are some dark blue places in there. And those are places where the motion acts like a wiper and takes off some of the peaks that I otherwise had created. If I look at it from the top, so again, this would be chips don't break out here on the left and along the bottom everywhere it's dark blue. Within this curve area, everything to the right of that, the chips break, but red would be a bad surface, dark blue would be a good surface. So like, for example, there's a place where if the oscillation is around 4 thou, the amplitude of the motion is around 4 thou, and I'm getting around a little less than half of a cycle of the motion per revolution, then the chips break and the surface is good, right? So that's a good spot. There's another good spot down here at about 6 thou and 0.3 waves per revolution. And they sort of go along a curve here because the timing is right to act like a wiper. That's why that is like that. So if I look at those surfaces, I can predict them, and what we measure comes out pretty close to the prediction. I'll skip past this table, but I'll show you some of the figures. What the surface looks like on the hemisphere that we did. So I can see the feed marks, and I see some variation in the surface roughness that is position dependent. But mostly it's pretty good, right? Blue, again, in this case, is good. So here it is shown for a cylinder. And again, I have to choose the conditions correctly. If I just randomly pick, the chips break, but it doesn't leave a very nice surface. And if I pick correctly, then the chips break, and at the same time, I also get a nice surface. So probably you have other questions as well, like what about the tool wear, or what happens to the temperature? We actually did some measurements like this. So at the top left, you see a setup with a thermal imaging camera looking right down on the insert during the cutting. The picture that's marked B is the video picture that the thermal imaging camera sees. And then down at the bottom right are the temperatures that we measured for a couple of different cutting conditions. And what I see is that when I modulated the tool path, that's on the right, the tool's a little cooler than when I didn't. And I sort of think about this like, you can stick your finger in boiling water, but not for very long, right? If you dip your finger in and pull it back out, then you can take it. And the tool can do that also. And that's kind of what's happening here. So in fact, we see a little less tool wear, particularly in difficult materials. So let's say like a titanium in this case, when it's interrupted, because the average temperature goes down, right? The tool is out of the workpiece sometimes and cooling off. You might ask me, okay, what happens with stability? And that's kind of an entertaining one. So whether or not there's chatter in a turning operation depends on the width of the chip. It doesn't really depend on the feed per revolution. It depends on the width of the chip. So in this case, I chose cutting conditions that were going to chatter in a normal turning operation. And I asked what would happen if I superimpose this oscillation. And what happens is when the chatter happens because the tool leaves a little bit of a wavy surface, and the next time around the workpiece, the tool plays that back. It regenerates the waviness. But if the tool loses contact with the workpiece, then the vibration has time to die out before the tool comes back into contact with the workpiece again. And so the areas that are marked in green here, this is where it chattered. And the areas that are marked in white are areas where it didn't chatter. And so in fact, this strategy, which we were using to break the chips, also turns out to be useful for chatter suppression. And I don't really have to get very far into the chip breaking zone in order to make that happen. So that turns out to be a good thing. You might have other questions as well, like isn't it damaging to the machine to have to make those motions? And the answer is no, because the motions are, from a machine perspective, low frequency and small. And they're the kind of motions that the machine is making anyway. Now, if I ask for bigger motions, eventually you get to a place where the machine can't do it anymore, right? If I said too high of a frequency or too big of a motion, I'll get to a place where the machine can't do it. And generally what controllers do in that situation is that they sacrifice the frequency for the position, right? They wait until the tool is in the right position before releasing the next block of data in the M&G code. And so they miss on the frequency, but they get right on the amplitude. It turns out that's okay because this diagram is much more forgiving in the amplitude than it is in the frequency, right? If the amplitude is bigger than about half of the feed per revolution, then almost for any frequency, it pretty much works. So that turns out to be okay. Okay, so where are we and what's coming next? So I'll say the system has been developed. It's been demonstrated both in laboratory environments and in production environments. It uses the axes of the machine tool to modulate the tool path so the motion happens along the direction that the tool was moving. So sometimes people might say it's like peck drilling. It's kind of like peck drilling, except that the pecking happens only along the axis of the drill. And in this case, the motion can happen in any direction that the axes of the machine can move. It's not like ultrasonic because the frequency of the motion is much less. But the conditions exist in a range that almost all machines can achieve that will absolutely cause the chips to break, regardless of the workpiece material, regardless of the tool geometry. I've seen it used in plastic and in aluminum and in titanium and steels and all kinds of stainless steels, all kinds of different difficult materials. The chip length can be selected within certain range. The instantaneous feed rate is higher to get the same material removal rate. The surface finish can be selected, but you sort of have to balance these conflicting requirements. Overall, the demand on the machine is not high. Most machine tools can do what's required. The calculations that we do are currently being done offline. Effectively, you give me an NC program, and I run it through a piece of software, and I send you back a much longer NC program that has those oscillations superimposed on it. But absolutely breaks the chips all of the time. Okay, so thanks for letting me present today. I'd be happy to take any questions that you might have.
Hey, Dr. Smith, I had a question. This is Kevin.
Sure, you can call me Scott, by the way.
Okay, thank you.
Sure.
Are you eventually going to be selling this software, or is it always going to reside with you to generate the program?
So the patent is owned jointly between Y12 and University of North Carolina at Charlotte. It has been commercially applied in several different companies. I'd really love to see it in a machine tool builder in the US. So far, not yet. But the calculation is straightforward. It could happen. The controller is powerful enough to do it. So I'd really like to see it in a machine tool builder's software, like chip breaking interpolation for turning operations.
So how do we just reach out to you and send you a current program, and then you modify it and send it back to us? Is that how it works?
Yeah, I wouldn't be the one to do that, but I'll hook you up with the people who would.
Okay. And I had one more question. I'm sorry, Scott. Does your rake angle have an effect on the chip break at all?
So, I mean, certainly the rake angle has an effect on whether or not chips break. And that's always true. But as far as whether or not this will work, no. Because this one works because the tool actually literally loses contact with the workpiece. The chip thickness goes to 0 because of what the axes did.
Okay. Thank you.
Yep. I see there's a question about whether this can be applied in a canned cycle. Yes. So again, I think in the same way, actually analogously to the way that you can have linear interpolation or circular interpolation to describe a movement of the tool, you could have chip breaking interpolation. And so that's movement of the tool along the path that you said it was going to move along, but superimposed along that path is this oscillation. Up until now, I would say the majority of users have utilized the technology by producing an NC program offline and then uploading the program that included those motions. Okay, I see a question about index Traub's chip master function. I don't know that one. I'll be happy to take a look. It has been a little while since I was at UNC Charlotte, and so I'm not sure about the scope of licenses that's out there. Would this work for boring on a vertical machining center? Yes. Realistically, any kind of single point operation that you would do on a lathe, okay, maybe with the exception of threading, this would work. Right, I think threading may be obviously not, because the motion of the tool is in a threading operation is along the axis of the workpiece, and I don't want to cut the threads, and so that cut through the tops of the threads, I mean. But yeah, it would work on a vertical machining center, yes.
Scott, how about OD grooving and ID grooving? Does this also work?
So if you're talking about a groove, like the kind of groove you would have for a snap ring, let's say, or like a parting operation, then yes, because all of that motion now would happen perpendicular to the axis of rotation of the workpiece, and so that's fine. That will work. And the same for ID grooving. If you mean a groove like a cylindrical groove, then yes, yes, that would work.
Thank you.
Okay, let's see what else. Can I share today's presentation? Yes. How do we contact you or your team? Certainly, you can send me an email, and I can connect you up with the people who would answer any other questions that you might have. What percent does the program get longer? 30%, 50%? No, probably more than that. Maybe like factor 5. It's a lot more motions, right? If you're just going to turn the outside of a cylinder, you know, the workpiece is rotating, and you tell the tool to move from position A to position B. That's one line in the program. And now what I'm saying is that I got to break that motion into a sinusoidal motion superimposed on top of that linear motion. So it goes a little forward, a little backward, a little forward, a little backward, a little forward, a little backward. It gets a lot longer. It used to be a problem. For the majority of machine tools that we have encountered applying the technology, it has not been a problem. The memory got cheaper, the processing speed of the controller got better, and that problem is more or less going away. Okay. Okay, that's all I see.
Hey, Scott, what are you guys working on now? What kind of cool things are you working on at the laboratory?
So yeah, there's a lot of cool things that we're working on. I'll tell you about the ones which are machine tool related. Um, so one that you might have seen recently covered in Modern Machine Shop is we're looking at other kinds of materials for bases of machine tools. Um, it's become more difficult to get large-scale castings in the U.S., and so do we have some other options for machine tool bases? And so one of the things that we did was to create a polymer mold using a big 3D printing machine that we have, and use that to create a concrete base for machine tool. And I actually showed the picture of that one at the beginning. That was the machine that had the throat that the part could pass through. So that base was made in concrete. Now, concrete-based machine tools, that's not a new idea. And there are lots of machine tools that use those currently, right? Some of the big high rail gantry style machine tools have concrete sidewalls, for example. But what was new here is that the mold was printed. And that allows a lot of flexibility in the geometry of the mold. So it's not something that I put together by hand, but it can include a lot of internal features and so on. And so that machine is under construction now. That was a photograph of it. It cut chips for the first time about 2 weeks ago. So we're excited about that one. I'm doing a lot of work in additive machining for subtractive operations. So I said that most, maybe all, additive operations still need machining, because if you don't make functional surfaces, then you're making things that look like things, right? But they're not those things. You need smooth functional surfaces on a propeller, or you need mating surfaces where things have to be joined, or you need threaded holes, or other kinds of things which are difficult to machine. But it turns out, if I think about the printing part like a preform, lots of people are trying to go, really close to the finished dimension. And sometimes that makes it worse because, well, maybe the part's not contained in the preform, or maybe it's hard for me to locate the part or to clamp onto the preform that was printed. If it's too flexible, it might not support the machining forces. So what kinds of things should we be printing, taking into account that I'm also going to do the machining operation? And I mean, that's sort of the whole premise behind design for manufacturing, is to think about the whole process. And so we're doing that, but if I think about it like additive for subtractive, what should those additive things look like? We're doing a lot of work in machine characterization, so measurement of what machine tools can do, what sorts of depths of cut and feeds and speeds you should choose based on the assembly. One of the big problems is tool makers sell tools, holder makers sell holders, machine builders make spindles, but it's not until you put all that together that you get the performance that you care about. And if you look at our NC programming infrastructure, it's sort of all focused on geometry. The tool's a milling, the tool's a cylinder, the workpiece is a prism, and as long as they intersect each other all in the right spots, you're done. That's not how it works, right? We have to live in the world where the physical world, and torque, power, stiffness, surface finish, all of those things really matter. So how do you bring those into the NC programming part of the puzzle? If you look at all the possible combinations of tool, tool holder, and spindle to try to get the performance, there's a lot. It's quadrillions of possible combinations. So how do you quickly figure out what your machine can do once you put your assembly together and then write the program that respects that, so that you don't scrap parts right from the beginning? So that's kind of cool. We're looking at machining of some real difficult materials, some new kind. There's a lot of material scientists at Oak Ridge National Lab, as you might imagine. And so very often they're coming to me with some new material. Can we cut this or can we cut that? So a lot of interesting metal cutting problems.
Awesome. Thank you so much.
You're welcome.
Hey, I'd like to respond to the person that asked about a recording of this. All of our technology team webinars are recorded and on the NTMA website. So I invite you to look at all of them. We've probably had about 10 or 12 so far, and I think the topics have been very interesting. And Dr. Scott, if I'd like to ask if you have anything else to add today, and if not, I appreciate your time and everybody else's time for joining us today.
I thoroughly enjoyed it. Thanks for having me.
All right, thank you so much, and have a great day, everybody.